Alright, so I want to go ahead and do a video here to explain the next math trick that we're going to use to help us solve some electrostatic problems. And this one we're going to start by talking about a couple equations that I'm not going to expect you to understand really the math behind, but I think it's a good idea to go through them anyway, just so you at least have seen them, and hopefully that can give you a conceptual understanding of what's going on here. And it's two of Maxwell's equations. That's the first one. This one's called divergence. It's the divergence of an electric field. It basically tells you how much it's spreading out. If you think of this in terms of flowing fluid, this basically tells you, like, if it's positive, it tells you how much is flowing out of a faucet, like how much it's flowing out and spreading out. If it's negative, it's essentially a sink, how much it's going into the sink, into the drain, I should say, maybe. It's going in. And so this just basically tells you the total amount of like faucets and drains that you have. This right here, this is the charge density. You know how much charge there is per unit volume, or sometimes unit area or length or something like that, but it's like a density of you know how tightly packed the charge is in an area. And then this is just a constant that deals with the Coulomb constant that you might be used to, is K equals 1 over 4 pi epsilon naught. And so this constant is just that one here. It's just part of the Coulomb constant, or really the Coulomb constant is made from it and the 4 pi, but it's the permeativity of free space. And then this is just what's called a del operator. All you really need to do is think of it as a vector that kind of takes the slope. When you do this operation here, this dot with it on a vector, it tells you the divergence. If we take it and do what's called a cross product with it, it tells us the curl of a field. And for electric fields, that's 0. So this one's called curl, and you can think of it really as how much it curls the field, how unequal it is. If you put something in it, how much would it cause that thing to spin or rotate? That would be the curl of it. And this one's called a dot product. It multiplies two vectors together and only multiplies the parts that are parallel. This one multiplies the parts together of two vectors, and it multiplies the parts that are perpendicular. Okay? So this multiplies perpendicular, and this is the part we're interested in here. Basically, it takes anything that's perpendicular to this vector, multiplies by anything perpendicular in this vector. And so if you look at that, you say, all right, well, if these two multiplied together like this, if I multiply all the perpendicular parts together and I get 0, what does that tell you about these two vectors? What it should tell you is that they are parallel. They have no parts that are perpendicular. All right, so just in reality, this, I couldn't draw it really as an arrow, it's more like an operator, but just pretend. We have this vector here has to be parallel to this vector. So both of these must be parallel if their cross product is 0, like it is for electric fields. Which then means that I can say that this electric field is just that first vector times some scalar, and I'm just going to call it a v for now. Right? That should make sense. So maybe here in this case, the way I drew them, it's E is equal to 2 times this del, this upside down triangle, upside down Greek letter delta. Maybe it's 2 times del, or maybe it's a half times del, or 3 times del. Whatever it is, it's some scalar times this other vector because they're in the same direction. And so what that allows us to do, it allows us to rewrite this curl equation like this. We can rewrite it as del cross del v equals 0. And so then what we're interested in is, well, what is this scalar here? Well, we've essentially just done a quick little math trick, and it turns out this scalar is essentially the, I guess you could kind of think of it as, it's really like a calculus 3 type thing, but the idea is that if you go everywhere in a space now, we're going to go through and we're going to replace this. So we talked about a field before where we had like a room or something, right? So we had some box or some room, and every location you go to, you go here, there's some vector at that point associated with it. It's called the electric field, and it's the electric field at that point, and it has a strength, it has a length to it, and it has a direction to it. And you go to the next point, and there's some other different electric field vector there, potentially pointed in a different direction with a different strength. And everywhere you go in this whole room, there are these vectors that are these electric fields, and they're pointed in different directions and things like that with different strengths. Some of them are weak, some of them are really big and strong. They're all different. Well, what we can do now is we can take this scalar and we can essentially go through our whole room. So we have that our same box now, but instead of filling it up with a bunch of scalars, we can fill it up with with a bunch of vectors with arrows. We can just go to a point and just have a scalar associated with it, just some number v. And then you go to the next point and there's just some other v. And then the next point and the next point. And we don't have to worry about them being vectors. We don't have to worry about their directions or anything like that, because vectors are hard to work with and scalars are very easy to work with. And if we do this, we fill this up with this v number, all these scalars. At every point has a different scalar to it. Kind of like if you went in a room, every point in the room would have a different temperature. The temperature doesn't have a direction. It'd be some scalar field. And we move to the next place and we measure a different temperature and a different temperature. But instead we're measuring this scalar voltage thing here, this v. All we would then have to do is go back and apply this del operator here to it like this, and we would get back our entire map of all our electric field vectors. We could go through and do that. And so the idea is, if we have this scalar field, can tell us everything we need to know about electric fields, but scalars are easier to work with, then why not just work with that scalar, just work with V, and then when it comes time to actually do something, you can just translate it back to electric fields if you have to. And then you can take that electric field and translate it back to a force if you have to, and figure out how everything's going to move and what stuff's going to look like. So that's the basic idea that we have. We found this scalar here through a quick little math trick that allows us to figure everything out. How do you get electric field from it? Well, essentially, this del acting in this capacity, when we took it and dotted it onto this, it was called divergence. When we curled it onto this, or we cross-producted on this, it was called curl. Here, it's called the gradient. And when it's acting on a scalar like this, it's called the gradient, and it's essentially telling us a slope, right? Like a slope of the scalar field. So you could imagine if I had, like, say I was sitting here and I had a certain voltage, let's just call it 3, and then right above it I had a 2, and right below it there was an 8, and right over here there was a 4, and over here there was a 5, and over here there might be another 3, and over here there might be another 4 and another 5. But if we went all the way around it and we looked to see everything that there was, and this is kind of a little hand-wavy bit of an explanation for it, but essentially if we took the gradient of it, the slope, the vector 3 calculus kind of slope, it would give us a vector that pointed in the direction that this was changing the fastest, and 3 to 8 would be the biggest change, so our electric field then would be pointed in that direction. And then of course how big of a change it was and how these other changes all occur would then tell us how long it was. So all of these numbers could be our scalar numbers, and then we just figure out how it's changing as we move through those scalar numbers, and that tells us this electric field. Okay, so let's go ahead and give this scalar a name. I've said it a couple times accidentally, but we're going to call this thing I represented with a V, we're going to call it voltage, or scalar potential. That's a name for it. You're probably not going to see it much at this level. Or electric potential, or potential difference. Now, the potential difference and the electric potential, you might hear some people say those are two different things. One is a change in voltage and the other is just the actual voltage. But I don't think that's possible. You can't have the voltage of a single point. You can really only talk about changes in voltage, just like you can't talk about the potential energy at a point. You have to have the potential energy at a point relative to some other point that you set as a 0. So I really think these two are pretty much interchangeable, but be careful that some people use them different. Or sometimes it's the electrical potential difference. I'm not going to write that whole thing out. Electric potential difference. So all these things are basically, you hear those words, they're talking about this scalar thing here, voltage. And I'm sure you've heard of this word voltage before. You know, you hear about something, oh, it's, you know, we've got this vacuum cleaner, it's 150 volts, or you've got this thing over here that's, you know, 20,000 volts or something like that. And that's what they're talking about. They're talking about this scalar potential for it. And so what is it now? We've described it mathematically. We said it's kind of this slope. How do you think of what this thing is? What do you know, it's not just some number. There is an actual physical interpretation for this math trick. And the way I think of it, my first thought of it, is that it is your potential. This voltage is your potential, hence the name we give it, potential, electric potential. It's potential to move a charge. It's your potential to move a charge. Now pay very close attention to that word, that it's this definition, potential to move a charge. So I like to give the example of, say you had you had two rooms, and in one room you had a skinny little guy, and in another room you had a super big, strong, big muscly leg, big muscly, big muscle guy, right? I don't know. I'm trying to draw a big muscly guy. Here you go. Big muscly guy standing in there, right? Big muscle guy. And I asked you the question, which guy here, the big muscle guy or the skinny little guy, which one's lifting more weight? And if I ask you that question, you would probably want to say, oh, it's the big strong guy. He is lifting more weight. But you have to pay close attention to what I asked you. I asked you who is lifting more weight. I didn't say who could lift more weight. If I asked you who could lift more weight, it would be the stronger guy. But I asked you who is lifting more weight, in which case you should say to me, I don't know. I can't tell you who's lifting more weight because I don't know who has weight available to lift. This strong guy could be in a room that has no weights in it at all. Maybe there's nothing in there for him to pick up, but this little wimpy guy, the skinny guy standing here, and he's got like a little barbell or something like that that's like 10 pounds, and he's picking it up, in which case he's lifting more weight because he has more weight available to him to lift. So there's a difference between these guys' potential to lift weight and how much weight they actually are lifting. It's obvious that the strong guy has a greater potential to lift weight than this other skinnier, weaker guy, but that doesn't necessarily mean that he is lifting more weight. And and it's the same thing with this voltage. This voltage number doesn't tell you actually how much charge is being moved. It can only tell you how much charge could be moved, the potential to move charge, if that charge was available. If, a big if charge is available. So you could look at something like a stun gun, like a little taser thing that you might buy for self-defense, right? Those little taser things, and they've got the little prong sticking out, and then the electricity goes between them, and it makes that cracking noise and whatever. And you use that for self-defense. And you look at some of those, and they'll tell you, oh yes, it's got 100,000 volts, right? But this thing is not designed to be deadly. You use it on someone who's attacking you or something, and it hurts, but it's not lethal. It doesn't kill them. However, if you look at your wall switch at home, right? You look at the wall plug, and this thing has 120 volts, right? 120 volts. And you think, oh, this 100,000 volts doesn't kill you. This 120 volts won't kill you. When in fact, that's not true. This 100,000 volts doesn't kill you, but this 120 volts, it could. It could really seriously hurt you. And the difference is that this guy is designed with a really high potential to move charge, but they don't design it with very much actual charge available to be moved. So this thing, while it can push electrons through you really fast, it doesn't have a lot of them to push through you. And it's the amount of electrons that are getting pushed through you that kills you, that stops your heart. So this guy can't really kill you unless you have like a pacemaker or some previous problem that it messes with. But this guy, much lower voltage, but there's a whole lot more electrons available, right, to come out of this and be pushed through you. That was supposed to be lightning bolts coming out. It's not very good. But anyway, there's a whole lot more here. And so though it has a lower potential to push the electrons through you, it has a lot more of them that it can push through you. And therefore, it can actually really harm you. Let's imagine, go back to this thing here. If I'm standing off to the side and these guys want to throw their barbells at me, this guy has a much greater potential to throw that barbell at me a lot harder and hurt me with it. But if he doesn't have any barbells available, then I don't really have to worry about him really seriously injuring me if he only has like small little like pebbles or tiny little things to throw at me. If this guy has like one big barbell or something he has to throw me, he has a bunch of these barbells, he starts throwing them at me, he can't throw them as hard, but if he has more of them, then he has the potential more to do harm to me. So that's the difference. One is, this guy could throw barbells a lot harder at me and hurt me with them, but if he doesn't have any available, he's not going to hurt me. That's like this example here. Big potential to move electrons, but not a lot of electrons available. This guy might have a whole pile of barbells or things over here to throw at me and hurt me, but he can't throw them as hard as this other guy. This has a whole lot of electrons available. It may not be able to shove the electron through me with as much force or as much speed and everything like that, but it has a lot more of them available to push through me and actually then hurt me. Okay, so that's the difference. You got to remember it's your potential to move a charge. It's not actually how much charge you are moving. And then the last little kind of definition way to think of it is that this voltage is potential energy per charge. And that goes right along with this potential to move a charge. It's your potential energy per unit charge. So it's the amount of potential energy you have then divided by the number of charges you have. Okay? So that's the basic idea behind potential or scalar potential or electric potential difference or voltage. And you got to kind of spend some time thinking about it. Make sure you kind of justify it in your mind and get a good understanding of that it's not necessarily telling you how much electrons and electricity is being pushed through something, how much charge is being pushed through something. It's how much could be pushed. You could have, 1,000,000 volts across a room and absolutely no charges are moving. Okay, because there might not be any charges there to move. You could have 1 volt across the room and you could have a whole bunch of charges moving across the room because it has because it has the actual charges there available to be moved. Okay, I think that's pretty much it for my little introduction of what is voltage, and hopefully you can kind of think about it and it'll make a little more sense to you as we move into actually using it with the equations. Technically, this is the first equation that we're going to use because we defined it as this, but we're going to go through and derive some more in the next video. All right, that's all for this one.